Yes, it looks great.
Great. So yes, good morning. We're going to talk a lot of stuff on precipitation type, one of my personal favorite subjects. And then we'll talk about ForecastBuilder and things going on with version 10. So we also have Ted Ryan listed on here. He is not able to make today's call because of a conflict. So let's look a little bit back at ForecastBuilder history. And you know, the whole program started, amazingly 5 years ago here in Central Region, and we had developed it because we really wanted to improve snow and ice consistency. Pre-ForecastBuilder, every office sort of had their own approach at doing this, and it resulted in a lot of inconsistencies and collaboration struggles and all of that. But to do snow and ice consistency, you had to, because there are so many different elements that go into making snow and ice, you essentially have to establish a consistent forecast process, including the precipitation type approach. We also had a mid-short range gap. There's a policy for ESTF, there's a policy for days 4 through 7, but nothing in between, so we needed to close that. One other problem that's existed, and they're still kind of relevant today, but maybe a little less, is that, when you go into service backup, it was always like, okay, what tool do I use to do this or that? ForecastBuilder is now there, and you have a common level of at least science and technology for the GFE operations to utilize. And also ForecastBuilder just helps reduce the amount of tools and individual procedures needed. The mission certainly has evolved since then. We've spread the wealth of forecaster expertise across the country. I mean, we're injecting stuff from Southern Region, Western, and Eastern, and they're utilizing some of our stuff too. So it's really, really awesome to see that. ForecastBuilder delivers the NBM and eventually here the CFP. And, ForecastBuilder also provides band-aids to the NBM because the NBM is on a longer-term update cycle because of the way that things are handled on the supercomputers. So we help provide at least some sort of a band-aid approach until those changes get involved in the NBM. So ForecastBuilder itself, just for your awareness, there are 2 groups that help support it, and they're all cross-regional. One is a SUE team that helps vet science and provide vision and recommendations. And then we also have this, I call it an ad hoc technical working group, basically people that have been interested in the application and help provide technical updates to it and any kind of bug fixes and all that, so that meets all the various regional needs across the NWS. So let's jump into precipitation type. There are 4 approaches in ForecastBuilder. They all remain supported here for this winter season. The first one we'll go through here is SnowLevel for our western portions of Central Region. It's a very familiar process. We've run it for many years, and so it's very easy. A lot of people, I think, even outside the NWS, understand the concept behind SnowLevel, so it works as a decent messaging tool. It handles P-type in sharp terrain. You can see the process as noted on the right, and you can utilize Prob Ice Present grid there to help with some of those upslope kind of freeze and drizzle events. Unfortunately, for those, I would say, more rare occasions where you get let's say an atmospheric river come across and warm air gets stuck in or gets aloft over cold air that's stuck in valleys, those freeze and rain events are not captured via the SnowLevel process. Then we have the top-down and Bourgouin methods. They are essentially the same thing as like lift and index and CAPE. Both approaches require the use of a Prob Ice Present grid to help tell you whether or not you have ice crystals to begin with in the clouds. If you don't, then you're just dealing with supercooled liquid water going down the rest of the profile. Continuing on down the sound, and you look for what's the warm nose, and the measure of that is max Whipple aloft and top down, and then positive energy aloft in the Bourgouin. The positive energy just is calculating basically kind of like a CAPE measure there, which is in joules per kilogram. Then the cold dome is measured by the Prob refreeze sleet grid in the top-down analysis, and then the negative energy low level in the Bourgouin. And then finally, the surface is reflected by surface temperature in the top-down, and then surface wet bulb in the Bourgouin. So And then all these variables come together to make the individual precipitation types of rain, snow, sleet, freezing rain. These approaches, I mean, they both have, we have Bourgouin approaches I'll show at the end in the eastern portions of Central Region. And, these are very familiar. We've had them around for several years, the top-down even longer than that. With the top-down, the benefit there is the NBM's got data for that, so you have a little more data sets in AWIPS than you do for the Bourgouin. But on the flip side, the Bourgouin is probably a little better for handling narrow, warm, cold layers than the top-down. There is some code in the top-down in ForecastBuilder to try and attempt to handle that, but it's not nearly as good as what the Bourgouin would give you. The important part of all these three approaches that I've described thus far is that they are all essentially a deterministic approach, and this is the number one concern with them. So if you look at this from a graphic example here, so whether you take SnowLevel, top-down, or Bourgouin, you're all basically taking all these sound-ins, and the data set, of course, varies from whether you're using the Bourgouin or the top-down or SnowLevel, but you create essentially one single composite sound-in, and you derive out probabilities of rain, snow, sleet, and freezing rain from that. That does not reflect any environment uncertainty, and if you have a bi-modal situation, you're going to get the wrong IDSS message out of it. And I'll show that here coming up. An analogy of this is like, I'm just going to take a tropical system and I'm only going to message the track of the hurricane and nothing about the cone. So this is something that the NBM Science Advisory Group had noted, because this approach was in the NBM for versions 3.0 and 3.1. In 3.2 and 4.0, the process changed. And now we look at, for each member, utilizing the Bourgouin top-down approach, creating a precipitation type probability for rain, snow, sleet, and freezing rain, and then blending each of those probabilities to get a final probability. This is a much more statistical and meteorological sound approach. It has more membership than, say, the Bourgouin approach in AWIPS. It also has, I think it has more membership than even like the top-down and the SnowLevel. Unfortunately, man, I tell you, it's like with precipitation type, there's never one silver bullet that is never issue free. There are problems. Even with more membership than what you have available to you in AWIPS, it's still small, especially compared to other elements. There's a lot more membership going into the POP and QPF, and even more membership than in the MAX-T, for example. So you do end up with a little consistency issue there. And then for NBM 4.0, to help with the downscaling process, it uses the bias correction to IRMA, but that in turn can result in a spurious freeze and rain. Bias correction is only done on the surface because the IRMA is only two-dimensional. It's not 3D yet. You can also create, there's also false freeze and rain produced in the NBM, because if you have a scenario with, let's say, a radiational coolant, you can end up with the freeze and rain from that. Meanwhile, you have another scenario that brings a warm advection snow. So you have, that's definitely not going to be, of course, then a freeze and rain. So you get this percentage of freeze and rain from that dry NBM member. And then model vertical horizontal resolution can cause problems here with the sharper terrain of the Western US in this approach. So let's talk about that membership. Again, this is more membership than what's in AWIPS, but again, it's still small. You got 16 members in the short term, drops to 8 in the long term. Something to keep in mind in this chart here is that all those that, like the European ensemble, the GEFS ensemble, the Canadian ensemble, those are all ensemble means and not the individual members. There's an approach here we're looking at for NBM version 4.1, and once the data starts posting, I'll alert everyone of that, and then we're also hoping to try and get that into AWIPS for you to compare. We're going to look at actually getting all the individual ensemble members, but we're going to use a little different technique versus the Bourgouin, and so more of that will be to come, and a lot of it's in testing mode, so we're just going to see how it does compared to version 4. So the other challenge here with the NBM is that it's now a probabilistic data set for the precipitation type. Meanwhile, our hourly temperatures, for example, are deterministic. So what you can end up happening is like freezing rain with a temperature of 34. Is that okay? Yes. There's actually two reasons. One, the FRAM, if you had a temperature of 34 and a dew point of, say, like 28, the wet bulb will be below freezing, and the FRAM will give you ice and freezing rain out of that. But you also have a situation where there's uncertainty spread in how strong the warm nose is, how cold the cold dome is. And an example of that is shown here at right, where some of the spectrum here would support the freezing rain outcome. And so you see that in the probabilities. Meanwhile, your NBM deterministic gridded T is, say, 34. There's a worthy read here. I have a link about back from 2014 about deterministic forecasts have to be physically realistic, and it sort of connects to this slide. Let's talk about bimodal situations. This happens, you have a group of models, say, that take a storm to your north, another group of models take your storm to the south. Obviously, they result in two different precipitation type outcomes, and that's reflected here. You'd have one cluster would give you snow, the other gives you rain. The NBM accurately provides this as a rain-snow mix in your probabilities. If you were to use the top-down or Bourgouin in this situation, you would end up with sleet and freezing rain. Obviously, a completely different IDSS message and an incorrect analysis on this situation. So, these do happen. You see it, you could see it in clusters, and so this is something to always be aware of as we go through the winter season. Watch your storm tracks, and if it's a bimodal situation, and making sure you get the right outcome. So I do want to show this all in a nice little table here, where I show all the various P-type approaches and talk about all these various science factors that you have to deal with. How many members are in there versus what's in the NBM. Do you handle warm and cold layers? How do you handle bimodal situations? Do you get false freezing rain? And you can see through this table, the NBM PoWT is where we would love to head for the best kind of science and statistical approach. But as we learned last season in the Central Region NBM PoWT test bed, that it's not truly easy to do that. There are some issues, and we already noted those earlier. And so this past summer, along the Central Region NBM, the results learned from that test bed combined with some, Southern Region has been working with the NBM PoWT for a few years, and they've gained a lot of experience. So we took both and helped inject that into ForecastBuilder for this version 10. And we're going to talk about that now. So version 10, we have that support again for all the previous precipitation type methods. We have new support here in workflow to utilize the NBM PoWT, including provides solutions here to handle the various issues identified. And one of them that came out of their NBM PoWT test bed in Southern Region has been doing is having an unconditional precipitation type step. And then this is analogous to a scalar weather grid, and I'll show you that coming up. There's been a few other changes, the updated GUI. I'm sure a lot of you have seen that now that you've installed version 10 for this expandable toolbar and restoring auto run functionality for most parts of ForecastBuilder. There's still a few that are problematic, and we'll have a fix out for that. And then we incorporated several technical bug fixes. Matt Belk has been doing some awesome stuff for us in terms of looking through the Python code and all that. So let's talk about the this conditional versus unconditional. First, I want to say that this concept has been with ForecastBuilder since its inception. A lot of it's been kind of in the background, if you will. We've been working with this whole conditional concept for a very long time with the existing techniques where all the probability of type grids have been conditional, and then when you go to create the weather grid, it makes it unconditional. And like this statement here says, conditional PoWTs are meaningless without using a POP. So conditional means if I were to have precipitation, what would that type be? And then when you get the unconditional, that means I'm going to also now include what's that chance of seeing precipitation. So let me jump to this next part. So when we go to unconditional PoWTs, it has some advantages. You, as a forecaster, actually get to see where the p-type is going to be rain and outputted in your weather grid. And it's a scalar version, so it makes it easier for manipulation rather than the ugly weather grid. And like I said here, again, easier edited in the p-type forecast. So the unconditional probability types are used here to create the weather grid. And, it's very easy if you just have one precipitation type. This is what's stated here on the slide is, again, something that's been in ForecastBuilder for a very long time, that the max value of one of the p-types has to match the PoP values, so that if you were to do, let's say we had 100% PoT snow, that's easy. You just go right with the PoP. But if you had 50% PoT snow, 50% PoT rain, and a PoP of 30, things get a little bit more messy. And this is example here for in winter weather. Your unconditional probability of snow then becomes 15. Your unconditional probability of rain is 15. If you were to apply that to the typical weather grid, those would be slight chance values, but the PoP is 30, so that's incorrect. So we have to bring the value for the weather grid up, and so one of these has to be one, or if in this case they're both equal, they have to be raised to be the value there for the PoP. One thing that was considered was, hey, let's just normalize these unconditional probabilities, but when doing so, it resulted in some of these bizarre, unworkable grids. So let's take a look at this whole unconditional stuff. So as noted here on the slide, whenever or wherever conditional probability types are greater than 15% and the PoP is greater than 15, then the unconditional PoP matches the PoP. But if you have multiple conditional probability types and one is much higher than the other, then the lower probability types will be demoted to this 15%. And let me show you this in a graphical example. So there's this upper-low situation going across Texas, and you go with, in its wake, maybe you have some loss of ice aloft, and so you start to introduce freezing rain and rain in that outcome. And so when you go to initialize the unconditional probabilities, these 15s will show up, and that's a reflection that these two items, the freezing rain and rain, are secondary precipitation types. And if you as a forecaster believe, hey, there's going to be ice aloft, you've looked at several guidance members and determined that yes, this is a situation where we're going to just keep that ice. You could just go in there and get rid of that 15 section, bing, bang, boom, those types are gone, and you're just left with the PoT snow. So how do you modify these unconditional probabilities? Well, first, to get them in the first place, you're going to hit a button that's called init all PoTs, and that gets the first guess. And it's going to show you where you have snow, sleet, freezing rain, and rain. And if, for example, let's say, given a scenario that you've done a lot of looking at various guidance and near term, better yet, let's say this is happening right now, and you see there's no snow or no sleet or freezing rain being reported in observations, you can just go up and go in here and delete those grids. And that gets them out of there easy. That's a quick way to get rid of that. But you may have to go in there, and let's say there are some observations reporting it, and you only want part of the area to have freezing rain and sleet. So then you go in there and just highlight which areas still have that remaining, and then zero out the rest of it. You can also go in and add precipitation types. So as a result, in ForecastBuilder version 10, we have a consistency check step. And that consistency check is there to ensure there's, your probability type, some max value is going to match that of the POPs, and that the probability types at least are somewhat reasonable for the forecast temperature, and snow level if applicable. You don't want to have some sort of, maybe a freeze and rain when your temperature is 45 or 50. That just seems really outside the spectrum. Similarly, a rain that's like at 15. That's some of these things that consistency check is gonna look at. The consistency check is also gonna get kicked off before you enter the accumulation step, just to be sure that happens. But we highly recommend that you run that, hit this button before moving on out of the unconditional precipitation type step. So when you run that consistency check, sometimes it will be like, hey, we got a problem. There's something that doesn't match. And so what it will do is I'll highlight your grids, and here's that, and that's shown here. And it's going to create some temporary grids to where say, hey, I don't know what's supposed to happen here. The good thing is the status bar will tell you, hey, here's a good solution that you can go for. And it'll say copy values for that to another grid, and there's various things underneath that edit section of this step to help copy that to that area. Or you can just go in here and get rid of these, like in this case, instead those are grid points where there's no probability type assigned, where the NBM had snow but your temps were too warm. Beyond this, when it comes to precipitation accumulation, all this still remains the same. I just want to provide a note here that the conditional grids will update, if you've made some changes there to the unconditional p-type. That just happens automatically, so that way when the precipitation accumulation reads in those conditional probability type grids, they are reflective of what changes you made to the unconditional. So what we're planning this winter for here in Central Region, we have basically restored things for the most part before what we did with the NBM PoWT testbed last winter. We do have 4 offices going to utilize the NBM PoWT within the ForecastBuilder workflow for this winter: Chanhassen, Duluth, Marquette, and Detroit. So it's a little smaller subset than what we had last winter, and that's okay. But we do encourage everyone, you should have like a ForecastBuilder _exp installed as part of a tech order. That one allows you to utilize it in practice mode and test running ForecastBuilder with the NBM in it, because that unconditional precipitation type step is only available when you are using NBM as a p-type approach. So I want to end this with a thank you. Again, as I said, ForecastBuilder is supported by, we have a lot of people on both the SUE and technical working group, and many of them are in this email address here. So if you have any questions on ForecastBuilder, you have ideas, suggestions, concerns, feel free to shoot an email there, and we will respond as soon as possible.